Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. We are going to discuss part 2 of wire electrochemical micromachining, that is abbreviated as wire ECMM. What we have done in the part 1 of the lecture on wire ECMM, let us have a relook on it. Introduction to wire electrochemical micromachining, we have discussed it. What is wire ECMM? The principle has been discussed. What is working principle of the process? That is, we work, this wire ECMM works on the principle of Faraday's laws of electrolysis, that has been discussed. How to calculate the material removal rate in this particular case has been discussed. Different variants of wire ECMM also have been discussed, for specifically what are the various variants and how to make use of this particular principle. What are the elements of wire ECMM system, not EDM, this should be wire ECMM system, that have been discussed in the last lecture. And photographic and schematic views of the wire ECMM machine tool have already been shown to you in the part 1. Different elements of the system, mainly power supply, electrolyte supply system, XYZ motion controller also have been discussed to some extent. Then process parameters and characteristics of the wire ECMM process have also been told to you in part 1 lecture of the wire ECMM. Electrolyte, conductivity K and type of electrolyte, voltage, current, feed rate, etc. are the various process parameters that affect the performance of the wire electrochemical machining and wire electrochemical micromachining processes. What we are going to discuss in part 2 of the lecture on wire ECMM, mainly we are going to discuss the applications and some part of the tool design of wire ECMM process was left, so that also will be covered before applications, and applications are specifically in aerospace industry, automobile industry, etc., that we will discuss in detail. And then finally we will discuss the conclusions of this wire ECMM process. Tool design, which was left in the part 1, we will continue with this one. You can see the different kinds of the tools. Here you have the helical tool that is shown over here. Now when it is rotating, it is agitating the electrolyte, which helps in the removal of the voids as well as sludge from the interelectrode gap. Then you have cutting edge tool over here. When it rotates, it also stirs or agitates the electrolyte, that also helps in the removal of the sludge. And the bubbles, some bubbles are shown over here as well as here, and they are quickly removed from the interelectrode gap because of this stirring action. And then you have fluted tool used in wire ECMM. This is the fluted tool used in wire ECMM. This is the movement, etc. You can see here, this is the workpiece, this is the tool, tube type tool, and this is the helical tool, enhances the flushing of electrolyte and electrolysis products from the machining gap. These are the velocity vectors which are shown over here. Simulation image showing electrolyte velocity vector in case of rotating helical tool, they are shown over here, and this rotation helps in the removal of sludge, as I have just mentioned. Tool design in wire ECMM. Tool design makes wire ECMM a two-step process. Also, mounting of such thin wires on the setup for processing is not very convenient. To overcome these problems, researchers have proposed the use of micro drill, cutting edge electrode and fluted metal tube in place of a flexible wire, improving flushing efficiency. I have already shown to you these things. This is the one, this is the helical one, this is the cutting edge, and this is the fluted one. Micro drill, the cutting edge tool I have shown just now, and easy to mount on a spindle and rotate at high RPM, that is 50,000 RPM. Why it's not difficult to really rotate at such a high RPM if you are using just the wire, simple wire. When a cutting edge tool is used, the average current density in the machining gap is reduced due to increase in inter-electrode gap in the zone facing the flat surface of the tool. This leads to the reduction in the side inter-electrode gap. In case of a fluted tube cathode, shown in figure C in the earlier slide, electrolyte is ejected from its micro holes. Workpiece is vibrated in the direction parallel to the axis of the tube to ensure uniform spread of electrolyte. This is very necessary, and the amplitude of vibration is kept more than the hole spacing on the tube. It is useful in machining of thick workpieces and also in preventing the electrolyte from flowing to the non-machining region, which results in stray corrosion. This is very important, that non-machining region, their electrolyte should not go, otherwise it will cause stray cutting, and if stray cutting is there, then it will affect the accuracy of the machining, and in some cases it may even affect the shape of the machine component. Process parameters and characteristics. You can see this diagram of process parameters and process characteristics. Process parameters, a power supply process parameters are pulse frequency, current value, pulse type whether unipolar or bipolar, pulse amplitude, duty ratio, voltage, etc. And when we say pulse, you can have different types of the pulse. I will tell you later on. You can have triangular, sinusoidal and so on, and all of them have the effect on the process. Workpiece thickness, electrical conductivity of the workpiece, composition of the workpiece, and that helps us in deciding what electrolyte or electrolyte mixture should be used, and then chemical stability of the workpiece with reference to the electrolyte. This is very important aspect. Workpiece should not react with the electrolyte. Then mechanical, motion resolution, wire traveling speed and feed rate, all the three are very important parameters. Then workpiece wire vibration amplitude, we have already discussed. You can vibrate the tool or you can vibrate the workpiece depending upon the requirement. And then wire tension. Then you have electrolyte parameters like type of flow, pressure of the electrolyte, composition of the electrolyte. This you have to decide according to the workpiece material, pure metal or alloy. Then flow rate of the electrolyte, conductivity K of the electrolyte, viscosity of the electrolyte and temperature. This viscosity is also very important of the electrolyte, as well as temperature is equally important because it is going to change the conductivity of the electrolyte. So you should maintain constant temperature in the bath or the inter-electrode gap, whatever you are using there, otherwise it will change the conductivity, and conductivity changes, then machining performance, machining features, dimensions will also change. Then tool wettability, tensile strength, surface textures, diameter of the tool, wire length, here wire is used as the tool, so length of the wire, chemical stability of the wire, profile of the wire. We have seen different profiles of the tool or the wire that are used in wire ECMM process. This was given by, this is known as Ishikawa diagram. Effect of some electrolytic factors at higher electrolyte flow rate, dispersion of gas bubbles and electrolysis products become more efficient. Electrolysis product is nothing but the sludge that is being formed during the wire electrochemical micromachining. A uniform current density in the frontal and side inter-electrode gaps is established, and higher value of feed rate can be used for machining purposes. As the charge carriers in the cell increase, the anodic dissolution rate gets accelerated. If the tool workpiece feed rate is not increased proportionately, then side inter-electrode gap increases and the machining accuracy deteriorates. If side inter-electrode gap is increasing, then our accuracy of the machine component is going to deteriorate. As feed rate is increased, frontal inter-electrode gap decreases and the replenishment of fresh electrolyte in this gap becomes difficult, because gap is small, pressure of the electrolyte flow is constant. So definitely less electrolyte flow will be there and it will be difficult. High electrolyte pressure also assists in dispersion of electrolysis products from the machining zone, and machining can be performed at a higher feed rate. And if you can perform the machining at higher feed rate, then definitely material removal rate is going to be higher. At high electrolyte pressure and high flow rate, the tension in the wire must be increased for stable machining. This is also important point, because the wire should be kept under tension all the time if you want to have good accuracy and if you want to avoid the sparking. Effect of power factors. Higher applied potential leads to an increase in MRRL as well as MRRV, because increase in potential leads to higher current, and if current is higher, then material removal rate is going to be higher, because we all know already that it is proportional to the current I. MRR L is proportional, L as well as MRRV, they are proportional to the current. In pulse power supply, pulse on time plays a key role in determining FM, that is the feed rate. Reducing the pulse on time decreases material removal rate. When you are decreasing the pulse on time, that means the total time for which current is flowing decreases, and if so, then definitely material removal rate, volumetric as well as linear, is going to decrease, and consequently the frontal inter-electrode gap also reduces, because if material removal rate is decreasing, then definitely inter-electrode gap, that is the gap between the wire and the workpiece, is going to decrease, because this recession of this workpiece in this direction is decreasing. If the feed rate is not reduced, the short circuit may occur, and we don't want the short circuit to take place, because it is going to break the wire, and reloading of the wire takes time, and if so, then definitely efficiency is going to be low. If for shorter pulse duration, smaller hydrogen bubbles are generated and they readily escape from the inter-electrode gap, thereby increasing volumetric material removal rate. On the cathode, hydrogen bubbles are evolved, and at the anode to some extent oxygen bubbles are also evolved. Ultra short voltage pulse of on time 20 nanosecond and duration around 160 nanosecond at a potential of 25 volt is tested in wire ECM. Please don't mind, this is normally written as nanosecond like this, and this is nanosecond like this. As applied potential increases, volumetric material removal rate also increases and wider curves are obtained or curves are machined. Side inter-electrode gap can be minimized by working at a potential at which is only marginally more than the tool feed rate to avoid short circuit, and in all the cases we should try to avoid the short circuiting. Linear material removal rate is given by following equation. MRRL is equal to 1 upon T duration integration 0 to T on time I upon EF into dt. So if you integrate this, you can get the linear material removal rate, where T duration is the pulse duration, that is on time plus off time, that will give you the pulse duration T on plus T off, and is the pulse on time, T on is the pulse on time, and E is the gram equivalent weight of the anode material. This E is the gram equivalent weight of anode material, and F, this is the F, I is the machining current, this is the machining current, and F is the Faraday's constant, and this is to be removed here. Higher machine Faraday's constant and its value is 96,500 coulombs, we have already seen in the earlier slide. So higher machining rate can be sustained without short circuiting with larger pulse duration. Effect of tool rotation and tool workpiece vibration. We have already seen that either tool can be vibrated or workpiece can be vibrated. Tool rotation initiates stirring action, that is agitating action of electrolyte. Electrolysis products are flushed out easily. Hence, a uniform current density is established in the machining zone. Relative motion between the tool and workpiece along the direction of the axis of the wire or the tool, here wire is the tool, also causes the electrolyte to flow in the inter-electrode gap due to viscosity. What is the effect of workpiece thickness? It definitely affects to some extent about the accuracy of the machine component. As workpiece thickness increases, frontal and side inter-electrode gap become larger. Electrolyte pressure along the workpiece thickness decreases due to drag force, and its replenishment becomes difficult in the deeper machining region, because as the machining thickness is increasing, then the taper of the workpiece keep on increasing, and if taper increases, then the machining accuracy decreases. It becomes inevitable to reduce the tool feed rate in order to avoid short circuiting. Tool workpiece feed rate. Increasing tool workpiece feed rate improves machining. Either you are feeding the tool or you are feeding the workpiece, depending upon the system that you have designed. So increasing tool workpiece feed rate improves machining accuracy in wire ECMM due to the reduction in tool workpiece interaction time. Because higher the feed rate, lesser will be the tool workpiece interaction time. It also reduces material dissolution from the workpiece in front and side inter-electrode gap, because total time available is reduced. Machining accuracy can be increased by increasing the tool workpiece feed rate. Tool workpiece vibration, either tool or workpiece vibration aids in uniform distribution of electrolysis products in the inter-electrode gap, in the machining gap, and it improves volumetric material removal rate. Once you are agitating it, vibrating the tool or workpiece, then uniform distribution of the sludge takes place in the machining zone or in the machining chamber. As a result of that, conductivity remains uniform, so you get better accuracy and higher material removal rate. Otherwise, you know what will happen, these electrolysis products will get accumulated near the machining zone and they will reduce the conductivity of the electrolyte, and if the conductivity of the electrolyte is reduced, volumetric material removal rate and linear material removal rate are going to decrease. That is why it increases the material removal rate or improve the material removal rate as given over here. This adversely affects the machining accuracy as the side inter-electrode gap also increases with an increase in vibration frequency and amplitude, but the uniformity of kerf also improves. This I have already mentioned to you in the earlier lecture also, that if volumetric material removal rate is increased, then if volumetric material removal rate is increasing, it depends upon the inter-electrode gap, and inter-electrode gap controls the current density on the workpiece. Effect of process parameters on machining quality, let us see it again. Power factor, for small pulse duration, large pits are formed due to high MRRV. If MRRV is high, then definitely the pit's size is larger as the pulse duration increases. Such pits are removed and polished surface is obtained. For very high pulse duration, the surface roughness deteriorates because of frequent short circuits, and I have already mentioned that we should try to avoid the short circuiting as far as possible to maintain good surface, machined surface and good accuracy. Optimal values of pulse on time and pulse duration must be experimentally determined for achieving high surface quality. Definitely experimentally you can determine it by conducting different experiments. Another way for optimizing the parameters is theoretically. So, I personally suggest to first optimize the process parameters theoretically and then conduct the experiment, and minor modifications here and there can be done with the help of the experimental results, because everything cannot be simulated, everything workpiece properties and other things cannot be simulated exactly. So, that you can do with the help of the experimental results. Tool workpiece feed rate, surface roughness is significantly influenced by the tool or workpiece feed rate. When the feed rate is low, time available for polishing of the surface is ample and low surface roughness is obtained. We always are interested, in most of the cases, not in all the cases, in low surface roughness value, that is known as fine surface, and high surface roughness value is there, that is known as rough surface. In certain application, definitely we need little higher surface roughness value to perform certain functions on the workpiece. Low tool or workpiece feed rate is preferred for achieving better surface quality, but then machining efficiency is usually compromised. So, you have to compromise between the material removal rate as well as the machining efficiency. Machining efficiency and machining accuracy, both they have to be, you have to see which is more important for you. Therefore, An optimum balance between the two must be maintained, that is the machining accuracy and machining efficiency or volumetric material removal rate. Tool workpiece vibration. High amplitude of tool vibration assists in flushing electrolysis products out of the machining gap and renewing the electrolyte more efficiently. This decreases roughness of the machine surface. Applications. Now we are going to discuss certain applications in other parts of the process. Features machined using wire ECMM process. Now you can see them very carefully. Different kind of the interesting features have been machined by wire ECMM process. You can see over here. Multi-layered 3-dimensional micro electrodes. You can see over here, these are the micro electrodes. You can see the enlarged view of these micro electrodes over here. This is the gap, this is the micro electrode, gap, micro electrodes, and so on. And the height of these micro electrodes is quite large, 2 millimeter here, 148 micrometer as the thickness between the two electrodes, and so on. So interesting application is there. Here you can see this square micropillar shaped surface texture. These are the enlarged view of this is over here. These are the square micropillars that have been shaped or machined with the help of wire electrochemical micromachining, and all dimensions of these micropillars are few tenths of microns, because this is the scale 200 microns. So definitely it becomes around 100 or less than 100 micrometer. Then you can see here interesting gear, micro spur gear that has been machined with the help of wire ECMM process, and this is the scale 100 micron. So you can slightly have the guess what should be the size of this gear, and this is the enlarged view of this tooth of the micro gear, and you can see over here the dimensions, and this is the radius of 62.50, and this is the thickness, that is 14.65 micrometer. And here you can see 3-dimensional hollow microstructure, very interesting, and it has been done in one go. You can see certain dimensions over here, and these slots have been cut in micrometer. Then you can see here serpentine micro channel for microfluidic applications. Now you can see how complicated and how difficult they should be to machine otherwise without wire ECMM process. So you can see over here, this is just the 9 micrometer thick pillar between in this particular gap, and this is another pillar, this is another pillar, and so on. So such a complicated features can be easily machined with electrochemical micromachining using the wire as the tool. And here is the fingerprint like coil spring that you can see over here, and this is the enlarged view of this particular part that you can see. So these are very interesting applications of wire electrochemical micromachining. Prospective areas of application of wire ECMM, where you can further apply this: sharpening of surgical plates, and if any burr is left, this is going to be very difficult, very painful, very harmful to the patient. So they should be deburred carefully before really using it, and you can sharpen them with the help of the wire ECMM process. You can see the direction of wire feed over here, and this is the blade cutting edge over there. Comb drive actuator used in MEMS. Now you can see different kind of this is the wire, and positive, this is negative, wire is cathode, workpiece here, this is made as anode, and this is the wire trajectory which is moving like this and cutting these slots, and these are the two parts, anchor, and this is the another movable electrode, and you can fit it here with few tenths of micron gap between these two plates, thin plates of 5 micrometer are there, and this is the overlap between the two. So such things can be made only with the advanced micromachining processes, not by conventional micromachining process. So machining of comb drive actuator used in MEMS, micro electromechanical system. MEMS is known as micro electromechanical system. It has many applications in MEMS and NEMS, nano electromechanical systems. Internal gear cutting, that is shown over here. You can make internal as well as external gears. So internal gear cutting is taking place. Here is the wire trajectory during machining. So wire is moving like this and it is cutting the teeth, internal teeth, internal gear teeth are there, and you can see over here workpiece is made as anode and tool or the wire is made as cathode over here, and it is cutting different trajectory on the workpiece. Now let us see process capability features machine using wire electrochemical turning operation, because wire ECMM can be used for different kind of the operations. Here I am showing some capabilities related to turning operations. As you can see over here, multi-step turning. This is a smaller diameter, larger diameter, still larger diameter. So different step turning operation can be performed with the help of the wire ECMM process. Here you can see taper turning. The tapered part, this part is clearly seen as tapered one, and that is the enlarged view of the same. Then threading is being performed, or threads are being made by wire turning operations, electrochemical turning operations over there. And here you can see the larger view of the thread form, that is enlarged view of this part shown over here, that is 1300 micrometer. Now this is the micro grooving. You can clearly see the grooves made over here. These are the grooves, they are clearly visible over here, that have been made over here. Then you have the indexed cutting over here, shown over here, triangular shape. This is the triangular shape that you can see over here like this, that has been made over there. And then you have the micro turning for micro grooving purpose, micro turning for micro grooving purpose. You can clearly see over here, that is shown in large view. This is the 100 micrometer, this is the 300 millimeter, then groove is there over there. So you can have different kind of the features made on the component by this electrochemical micro turning process. Then other proposed areas of application of wire EC turning operation, because all kind of operations or the possibilities have not been explored using wire electrochemical micromachining. So some of the areas have been proposed by Vyom Sharma and Dr. Ram Kumar of IIT Kanpur. So I will show you some of them over here. You can clearly see this is the dental implants, where you can use this particular process for making these threads, etc., and for even finishing the implants over there. Then you have this another one, minimally abrasive devices used in surgery. They can be machined. You can see wire is there, electrolyte is being supplied over there, and you are creating the different kind of the features over here like this. This has diameter has been turned, reduced over here, and you can make such kind of the product with the, this is the workpiece, this is the wire, electrolyte is being supplied, and you are forming this kind of the, this is the size that you are forming over here. Then you can do internal surface finishing of thin wall tubes. This is the thin wall tube and this is the wire, and you are finishing this internal surface by this particular process. It is very good, electrochemical micromachining, electrochemical micro turning is very good for finishing purposes, but it requires proper kind of the electrolyte to be used and optimum machining conditions. You can use it for finishing purposes very well. Then wire electrochemical micromachining for texturing operation, and these experiments were performed at IIT Kanpur by Dr. Divyans Patel, Dr. Vyom Sharma under the guidance of Professor J. Ram Kumar. Textured workpieces are shown over here. This is the original workpiece, and you can see this is the texture that have been created with the help of the wire. While taking one cutting in this direction and another cutting in this direction, you can create the micro pillars over here on the solid workpieces. That is what, and this tells you the inclination angle, this angle CA, quite 86.8 over here, but it has increased to 130, that is known as CA, means contact angle, and you can see here 134 degree, 133 degree. So from 86 to 134, this is very much important for creating hydrophobicity in the component, hydrophobicity, and this is needed at many places. And you can see that this contact angle has increased to 140 degree, that you can see in this particular case. These are all textured workpieces, and here it has gone to very high 147.6 degree. So what I mean to say here is you can create hydrophobic surfaces using wire, electrochemical, micromachining, electrochemical, micro texturing of the workpieces. Some research areas in wire ECMM, they are also very important, because we really need to do good research based on scientific principles. That is very much needed. Just technological research is very good, most welcome, but we also need to go into the science of wire ECMM process. A qualitative comparison of wire ECMM and wire electric discharge micromachining and electric discharge machining I have discussed in other lectures about the wire EDM process. Please see it carefully, very interesting one. You can see here machining time for identical machining length. You can see here these are the three high speed wire EDM. This particular feature has been created, and this is the surface texture that has been for this particular area, and this is with low speed wire EDM process, and this is the surface texture of this particular part shown over here, and this is the multi-slit wire electrochemical micromachining, and for this surface, this is the surface texture over here. So now some comparison has been made by Vyom Sharma, Dr. Vyom Sharma, during his PhD work. That is what I am going to represent here. For identical machining length, B, that is this one high low speed wire EDM, it is taking 25 minutes, which is less 30 minutes is this one high speed wire EDM, and 60 minutes for electrochemical micromachining, that is this part. So it is taking longer time, but giving the better surface texture. Machining accuracy in A, it is lower than C, lower than B. Machining accuracy is high in case of low speed wire EDM, and it is low in case of A, that is high speed wire EDM, and this is medium in case of wire ECMM process. Recast layer, it is none in case of ECMM process, because there is no heat generation, no recast layer, but slight in case of low speed wire EDM and serious in case of high speed wire EDM. Same way surface roughness, it is quite good in ECMM process, 0.37 micrometer, slightly better in case, slightly poorer in case of low speed wire EDM and very poor in case of high speed wire EDM. So this way you can compare wire ECMM with wire EDMM processes, but both processes have their own merits and demerits, and depending upon your component requirement, you have to choose the right kind of process and right kind of parameters, and you should optimize the parameters. Methods of enhancing mass transport in wire ECMM. Mass transport means you are going to enhance the material removal rate. Now axially vibrating the tool, this is the tool, and if you are axially, you are vibrating it in this direction, you can see here this is the time instances T0, T1 and so on. You are machining it continuously, direction of tool feed is in this direction, and this is the workpiece shown over here, that is shown over there, and you can see the velocity profile over here. Maximum electrolyte velocity at tool surface, this is the profile for the tool velocity, and it is maximum at the tool, and here you can see here it is almost 0. Axially vibrating workpiece, this is here you are vibrating the tool, here you are vibrating the workpiece. You can see here this is the tool, that is the wire, and you are supplying the electrolyte over there. This is the workpiece, and you can see here this is how electrolyte is flowing when you are vibrating the workpiece. Direction of tool feed, that is in this particular direction, that you can see here itself, and this is the enlarged view of this part that you can see over here. Both tool and workpiece are vibrated. I have told you in sometimes back also that you can even vibrate both tool as well as workpiece, but normally it is either tool or workpiece, but in some cases you can do for both. And this is how you are doing it, and this is the one, and tool and workpiece both are vibrating, so it is shown displacement over there with time. And you can have monodirectional traveling wire, it is traveling in this particular direction. So you have seen that you can vibrate the tool, you can vibrate the workpiece, or you can vibrate the both, and how the profile of the velocity of the electrolyte at different location is varying. Prospective areas of research further: machining with partially insulated wire for minimizing radial overcut. This is very, very important, because normally in almost all cases you are using the bare tool, which is resulting in stray cutting in wire electrochemical micromachining. If you can minimize or avoid stray cutting, then you are going to get the best performance from the wire ECMM process, and you will get very good tolerances. Now you can see here partially insulating wire. I know for clarity that it is very difficult to insulate the wire partially, not fully. Fully you can do it, but partially you have to insulate, because you want electrochemical micromachining also, and for that you have to have certain bare part from where current will be flowing between the wire and the workpiece. So you can see here different configurations are shown over here. This is the fully bare tool. You have large overcut over here, right, large radial gap between the workpiece surface over here, and this is the tool. Tool insulation half up to 180 degree, you can see here, and again the gap here, you are removing the material because current is flowing from the bare part of the tool like this, but there is no current flow from this portion there is no current flow. So material is being removed from here. So you know, kerf width decrease, first thing, and second thing, accuracy improves in this particular case. But if you can insulate say to 150 degree, then only this portion is removing the material, only this portion current is flow like this, and only this portion is removing the material, so you get better accuracy. Here it is only 90 degree theta 3, this is 90 degree lead, that means 270 degree approximately you are coating it. This is the 60 degree bare part, that current is flowing from this part to the workpiece, and this is only the 30 degree bare part. So smaller you can do, better you can have the perform, but you have to really evaluate in which case you are, because machining efficiency is very important. So material removal rate will decrease as you are increasing the coating on the wire, and for that purpose you have to optimize again for how much angle you should do the coating, and so that you can have the proper cutting of the workpiece, because accuracy, quality of the cut, as well as the time, all are important. It's not only quality, because it cannot take too long time, otherwise it will affect the process performance. Further research areas you can see here. Now lot of research is needed in this area, so one can take up this, and scientific analysis also very important in this particular case, especially the flow of the current and stray cutting. Machining with different waveforms of pulse voltage signals, because here you are going to use the pulse power supply. In pulse power supply you can have it continuous wave or pulsed wave with different shapes. I will show you some of the shapes that have been used. You can see here, this is rectangular pulse, this is the sinusoidal pulse, and this is the triangular pulse, and all the three pulses are going to give different material removal rate, different quality of the machined surface. Although machining time may be the same, voltage and current may be the same, they are going to affect finally the quality of the machine component. You can see over here, this is with the rectangular pulse, this is with the sinusoidal pulse, and this is with the triangular pulse. So minimum width, kerf width is obtained with the triangular pulse, and maximum kerf width is obtained from the rectangular pulse in comparison of these three types of the pulses. So this is already tried by different researchers, especially at IIT Kanpur and some other universities also. Now yet to be tried are so different shapes of the pulses are shown here. You have to have the proper controller so that you can get these kind of the shapes. So this is the trapezoidal shape, it is different from this rectangular shape. Then you have the left hand, right handed triangular shapes. You can have this kind of the triangular shape, or you can have the right hand triangular shape like this. So they are also, they may give different types of the performance of the process. We have not conducted, at least I am not aware of anybody who has conducted the experiment with these types of the pulses. Then you have the Gaussian pulse, which is different from the triangular pulse, and performance we do not know. Then you have the negative biased pulse, that is here is the negative biased pulse, and here it is the T on time, and this is the T of time. That may give different kind of the characteristics of the machine component, I don't know. Then you can have stepped pulse, that is another type. So what I mean to say here is that you can conduct the experiments with different types of the pulse and optimize the performance, and it depends upon whether you are more interested in material removal rate or lesser or smaller tolerances or better quality surface. Conclusions: wire ECMM is a promising technique for micromachining. This is because thermal and mechanical properties of the parent material remain unaltered after machining, because in wire ECMM you are not generating any kind of the heat. So there is no thermal effect and no mechanical forces are acting, so no mechanical effect is there on the machine component, which is contrary to other conventional and even non-conventional processes. Machining accuracy, efficiency and quality in wire ECMM are influenced by electrolytic factors, power supply, tool, workpiece material and thickness, and tool workpiece feed rate. We have seen all these things. Tungsten is most widely used tool material because of its high tensile strength and excellent chemical stability. Ribbed wire, textured wire, helical tools, cutting edge tools and fluted tools have been used for enhancing flushing in wire ECMM process, and most of the work has been done by Dr. Swayam Sharma at IIT Kanpur in this direction. the use of CNT, carbon nanotube wire, is limited due to its poor electrical conductivity, but this has lot of potential. If you can enhance the electrical conductivity, you can get much better performance, and they are very strong despite having excellent tensile strength and wetting property. Two-dimensional numerical models based on finite element method for anode profile predicting in wire ECMM are proposed. Not much work or hardly any work has been done in this direction. Finite element method has been proposed, has been commonly used for tool design as well as anode shape prediction in electrochemical machining, but it still needs to be explored in electrochemical micromachining, including wire electrochemical micromachining. These models determine spatial distribution of electric potential in the simulation domain. At present, commercially available multi-physics software are used for performing such simulations. So they can be used so that your total energy input in development of the system reduces, because you are going to use readily available software. And then wire ECMM is also used for the machining of cylindrical workpieces. We have already seen it, say turning of very thin wall tube, which is otherwise very difficult by conventional method. And finally, the capabilities of wire ECMM are successfully demonstrated for texturing on flat, electrically conducting and large surface area. These are the references. Some of references you can refer, use them. Thank you very much.